feeding AI today are getting bigger and bigger and bigger and more unwieldy. Quantum computing is going to help us wield that data significantly better and in a more controlled and precise way.
And thank you for taking the time to be with us. Let's get our bearings here, because we are going to talk about two topics, quantum and AI, which two areas of technology where there's still a lot of confusion. But simply, quantum machines solve problems faster than classical computers, and they've got great potential use cases in areas like drug discovery and climate modelling. Very much so. Now,
I'm going to say not faster, but different.
Different, yes, for sure. Now, it feels like many of us have as much an understanding about quantum machines at the moment that people did in the early days of computing about PCs and networks.
Yeah.
Right? It just very much feels like we're on the cusp of something big, but there's a lack of understanding around what quantum computing actually is. So let's start right from the beginning, because we don't want to make any assumptions about what people know in the room. So what is a quantum computer and how is it different from a classical machine?
All right. Well, if you start from the beginning, you've got your classical computer, which is, in the simplest terms, uses bits, and you've got ones and zeros. A quantum computer has qubits, where ones and zeros can happen at the same time, and that's called superposition. You can also take two qubits and entangle them such that if you separate those qubits and then observe or measure them, their output is correlated without necessarily communicating. So if you're really confused at this point, that's okay. Because even Einstein didn't understand entanglement and why that happened, and we still can't explain it. So it's all good. I mean, Einstein used to call it spooky action at a distance. So we still haven't figured that one out, but we know how to control a qubit to a point. We'll get there. We'll get to that. And we know how to bring those together into a quantum computer to create or to calculate and solve problems far greater and complex than a classical computer ever could. So because you can imagine you can do ones and zeros at the same time, and this coupling of superposition and entanglement means that a quantum computer can solve problems that crunch huge amounts of data and solve hugely complex problems that a classical computer would take 100,000 years to compute. A quantum computer will take, I think it was 500 seconds for that same problem. And to your point, it works very differently. It works on the basis of probability. And so you might have billions of permutations of outcomes for a particular problem. And that's pretty good, because what will happen is it won't give you a precise answer. It won't say, this is your answer. It'll say 99.99% chance it's this answer. So if you go from billions and billions of permutations to maybe 100, that's manageable. And you can work that one out pretty quickly. So it is different. You do use different use cases for a quantum computer than a classical computer. And when we do eventually have a breakthrough, you'll end up with hybrid systems. So classical computing is not going away, but quantum computing is going to absolutely supercharge what we know today, including AI.
Yeah, no doubt about it. Now, when we spoke the other day, you told me that at the moment, we have noisy intermediate quantum machines that produce a lot of errors because qubits can be easily disturbed.
Yes.
Right, unlike classical computers. Yeah. Now, there's decoherence, and that's loss of information from a system into an environment, which is a big issue. But issues around cooling these machines, right, which are potentially processing trillions of operations per second.
Yeah.
So a relatively small number of qubits requires enormous amounts of cryogenic hardware.
Yeah.
These challenges make quantum machines difficult to scale, but what needs to happen now to overcome this so we can get to the point where we can scale them to the point where we need to?
So this is important, because when will we have a quantum computer big enough to start crunching problems that are truly useful? Because at the moment they're still quite small, and they are crunching interesting problems and some, interesting, I'm going to say borderline solutions, so to speak. So the financial services industry are already starting to play with quantum computing because it helps with optimizing, say, your portfolio in various optimization problems. But they're sort of edge use cases at the moment. If you're talking real breakthroughs, we're probably talking 5 years. And why am I saying 5 years? We are getting to the point where there are lots of challenges in scaling quantum computing. So when I spoke about a qubit, it is very, very sensitive. When you spin it up into a superposition or an entanglement, anything like the slightest little thing will disturb it and make it collapse. So radiation, sound, and radiation is light, it's heat, and we're talking a lot of the quantum computers today cool these small amounts of qubits down to the absolute zero or below the temperature of the planet Pluto, to give that an idea. So the infrastructure that they need is extremely expensive, and there's an enormous cryogenic infrastructure required to do it. In fact, if you look at the infrastructure we have today, there are breakthroughs every day happening, by the way. So I think this is going to move very fast. But to cool a number of qubits required to power a fault-tolerant quantum computer, you're going to need 1 million qubits, which for those of you who know a little bit about the topic, that's 1,000 logical qubits, and the rest are, they protect your logical qubits. And to do that, you're going to need cryogenic infrastructure the size of like two skyscrapers. So not very practical or pragmatic. Yeah. And the hardware required needs to be so perfect at the molecular level. You know, when we're talking about photonic chips, for example, you know, the manufacturing methodologies required to do that are so niche and unique, because otherwise it'll disturb the system, etc. So we're talking some really challenging problems, and they're slightly different for slightly different types of quantum computers. So you can spin up a qubit using lots of different methodologies, trapped ions, for example. Superconducting qubits are probably the most popular with the big tech companies like Google and IBM. And then you've got photonic qubits, which is the qubit of choice of PsiQuantum.
Yes, and that's the co-founders of PsiQuantum are Australian.
Yes. Jeremy
O'Brien and Terry Rudolph.
Yes.
And the federal government and the Queensland government has chucked in $1 billion for PsiQuantum to build the world's first fault-tolerant machine in Brisbane, of all places.
Yes.
So does this mean that Australia will potentially lead the world on the quantum front? It seems like our government is willing to make, I guess, the investments that need to be made.
100%. They're doubling down, and PsiQuantum have committed to a 5-year time frame to deliver this, which is massive. There's a bit of confidence backing that $1 billion investment. They're Australian founders. They're an American company though, and they have got partnerships with all sorts of companies around the world. They've had the amount of investment that's going into this company is mind-boggling. And I think Australia has put its hand up and says, yes, we don't want to be fast followers on this stuff anymore. We actually want to lead in front. And I think some of the narrative is really interesting. They're sort of talking about computer chips, and they're like, oh, we were fast followers, but now it's Taiwan who is one of the leaders in the world. They're a small economy, and yet they're leading the way. Why can't we be that for quantum? And so that's the narrative. I certainly hope that we can do that. We do bat above our weight in quantum capability in Australia, which is really interesting.
Because you hear a lot from the universities around it too,
Yeah.
Sydney Uni and UNSW. I remember when I was a journo, I used to get press releases from Sydney Uni all the time about quantum breakthroughs. Couldn't understand what they were talking about, but I used to get them.
Yeah. Michelle Simmons won Australia of the Year a couple of years ago.
Yeah. She did for the work that she did on quantum computing.
Yeah.
Now, I'd like to know where quantum machines are going to provide the most value. I know I touched on drug discovery and climate modelling and that type of thing. I mean, we're not going to use them for simple things like email and word processing, of course, but talk about where you think initially the greatest applications will be.
So I touched on this earlier, but it's you're talking about areas that require the crunching of massive amounts of data. It's from a data and AI perspective, you're talking much more complex models. It'll allow you to integrate different data sets from vastly different sources, and be able to, it can manage the complexity, I think is what I'm trying to say. And so some of the use cases include fertilizers. So like nitrogen, at the moment, to commercially produce nitrogen requires enormous pressure and heat, and it's hugely intensive from an energy perspective and a manufacturing perspective. But nature does it naturally. You get plants that'll give you nitrogen like that. How is that possible? You know, that question. And there's billions of permutations as to how that's possible. Whereas a lot of scientists are pretty confident that a quantum computer will be able to ultimately give us nitrogen in ways that is naturally produced, or at least more easily produced. Another one is climate modeling. You can imagine the millions, if not billions, of data and inputs that are required to start accurately modeling data, climate projections, all sorts of things there. So that's another one, I think, the finance industry.
Climate modelling is a good one because I think that it's going to give us projections that we don't have now.
Yes.
Right, because it can crunch so much data, and maybe governments will start to wake up and realise what the extent of the problem. And it can't happen too soon, right?
Yeah, absolutely. And the other one with the pandemic just behind us, when it comes to spinning up new materials and pharmaceuticals, it'll be able, at the moment, the best methodologies that we have are to test and trial and put it out there and go, we think this is what's going to work, and then we test and we go, oh, that one worked. And it's a little bit, you know, I'm sure there's it's a little more precise than that, but fundamentally it takes years to spin up an appropriate vaccine or appropriate medication, whereas quantum computing will be able to say, well, we're 99.9% sure it's going to be somewhere here. And that'll speed up the process enormously, and we'll be able to spin up all sorts of new materials and medications.
Now, Claudine, you had to play with IBM's quantum machine.
Yeah.
How did you find it? I mean, was there a learning curve?
Yeah, absolutely, absolutely. Yeah. So, but all this stuff isn't hard. I mean, I think quantum physics is hard. I'm going to put it out there. I gave it a shot and I was like, oh my God, this is hard. But quantum computing is, you know, it's a language you learn like I think any other language. I think if you're familiar with coding, I don't think it would be something that would be beyond the reach of anybody in this room. You know, there's some fantastic materials out there. Terry Rudolph, who you mentioned earlier, if you're starting from ground zero or something, he's actually written a book called Q is for Quantum. And actually you can go to qisforquantum.com. It's a free book, it's online. It's not very long. And it goes through the basics of the concepts and the theories behind it. And you get sort of the end of the book, and then you understand how it all sort of comes together in the context of a quantum computer. And then if you go to IBM Q, and there are plenty of other websites, by the way, it'll walk you through, there are free courses online as to how are you supposed to code a quantum computer. Once you understand the concepts, you know, why entanglement is important, what it means to spin up a qubit, and it's actually not as complicated, so long as you're not trying to understand the underlying the underlying physics, which is really hard, and Einstein can't crack that one. If you just want to understand how it works for a computer, anyone can learn. Anyone here can learn that stuff.
For sure.
Yeah.
Now, organisations need to prepare right now for two key scenarios. The first is that quantum and AI together can be very powerful.
Yes.
And that's because, as I said earlier, quantum machines can provide the computational boost that's required for AI. Right?
That's it. Yeah.
To a big level. So how do you see both working together in the future in this scenario?
Yeah. So it won't be the first, I'm going to say, breakthrough in quantum computing.
Yep.
It might be the second or the third wave, because quantum computers are going to have to become a little bit bigger. But fundamentally, you know, you're looking at being able to crunch data to feed machine learning algorithms in ways we've never seen before. So if you think, you know, large language models feeding AI today are getting bigger and bigger and bigger and more unwieldy, quantum computing is going to help us wield that data significantly better and in a more controlled and precise way. so I think that's going to be transformational. I think we're going to get to a point where they're going to help each other almost. So you've got AI that will help, I think, in terms of managing the energy required to feed LLMs, the energy required to feed quantum computers, and then on the reverse side, quantum computers are going to start crunching larger and larger volumes of data to solve more and more complex problems. So I think ultimately they're going to feed each other. I mentioned earlier, it's not going to be classical or quantum. It'll be hybrid. And I think you're going to see that breakthrough moment within, give or take, the next 5 years.
Yeah.
Plenty of time to learn.
That might be being a bit generous, I think, maybe.
Generous? You think so?
Yeah.
Well, it depends. You're right. It depends what expert you want to listen to. Take your pick. So some experts out there think that there are government organisations from various countries, name their names, who may have already cracked it, and they're keeping it close to their hearts. It's a national security issue. The biggest burning issue beyond the opportunities we just talked about is actually cybersecurity, because and this could be also an area where chief data officers may need to collaborate with their CISOs, because once the quantum computer is big enough, it'll be able to crack Shor's algorithm, and that underpins all our cybersecurity protocols that protects our data. And so the questions along the lines of, do you know where all your data is? Is it logged and classified in ways that you know exactly where it is, how it's stored, how it's protected? That's something you can start now. It's going to take a while.
So people should start mapping their data.
Absolutely.
Practices, because hackers are in waiting, I'm sure.
Absolutely. And there are ways. You don't actually need a quantum computer to protect from yourself from a quantum computer. You just need better mathematics. And that's quantum resilient algorithms. And I think Telstra's already applying some of those. Combank, these are all sort of in the public domain. So some of the much larger organizations are quietly implementing these algorithms to protect their data, because it's well documented that bad actors out there are harvesting data right now. They can't decrypt it, but they think that they will be able to within the next 5 years, definitely 10. And if you think about the amount of time you need to keep your data, it's at least 7 years for tax purposes. And we know from recent breaches, companies tend to keep data for a lot longer than that, and that data is sensitive. So if you're not starting to assess and protect your data today, when a quantum breakthrough happens, you could be vulnerable back in time, so to speak.
How's the market going to decide, I guess, which breakthrough has the most legs, I suppose? Like, which quantum breakthrough is one that people need to really keep pursuing? Because there's lots of discoveries being made, right?
Yeah. And honestly, I struggle to keep track of them.
Yeah.
Every week there's a new breakthrough, there's a new discovery. I imagine there are even more that go on behind the scenes from a defense perspective. Yeah. I mean, you look at the likes of AUKUS, and there are 3 pillars in AUKUS, and one pillar is quantum. And so I reckon there's all sorts of breakthroughs going on that we don't even know about.
Yeah, sure.
So
forgot about that.
Yeah, yeah. And so, if I were to break down the breakthroughs, there's going to be breakthroughs in infrastructure required. So I talked about the hardware and how they have to be near perfect, not at a molecular level dint in your chips kind of thing. So that's challenging at scale. Creating one perfect chip is fine. Trying to do that at scale is a whole other challenge. The cryogenic infrastructure we talked about. And then you've got the challenges, and there are lots of breakthroughs, I think, in error correction. So you think about when you pull a quantum computer together, it will crunch lots of different algorithms. And because of the nature of how sensitive those qubits are, there are inevitably going to be errors. And so you can correct through those errors through other algorithms. So they're discovering and thinking of new ways of, and more effective ways of doing that every day. I think I'm missing one. Oh, and simply breakthroughs in and coherence. So I sort of touched on how sensitive it was. How do you keep your qubit coherent, as in superposition and entangled for longer? Because the longer it's coherent, the more gates and more computation you can perform on it. And that's different for every modality. So I sort of touched on superconducting qubits. All the companies have chosen something different, and they each have their unique challenges. Photonics is psi-quantum. Trapped ions is Michelle Simmons' modality of choice. So I think you're seeing breakthroughs in each of those fields every day, which is
for sure,
really
very
interesting.
exciting future.
Yeah.
I think we've got 10 minutes. I think we'll throw to questions. Who has a question for Claudine? I know it's a complex and heavy topic, but somebody must have a question. Yes, Shane.
Yeah. In case some people didn't hear that, does quantum computer create explainability issues? So that's a good one. That's a very good one. I need to think about that one. I think it's similar challenges. I'd imagine there are similar challenges to AI, to be honest. And it's going to come down to the data that you feed into it and how you structure that and understand, how traceable and is that data. If I think about it, it's going to come down to quantum computing in itself is not going to cause the issues. I think the issues will be in the data you feed into it and knowing where it came from, how it's structured. That will be the challenge. And I can see a lot of similar issues with Gen AI. Yeah, I think it's avoidable, but not without a lot of work. Yeah.
So we've got a mic. We've got a mic coming up there, Michael.
I love this topic. It's awesome. Thank you.
Great.
Yay. One question for you is let's say that we get some kind of breakthrough in quantum over the next 5 or 10 years, and we figure out what we can do with it and how to integrate it. The national security concern not goes away, but kind of goes in the background.
Yeah.
Do you see this industry being similarly concentrated as the AI industry is fast becoming, whereby you've got a couple of providers, in this particular case, probably IBM, and they've been talking about qubits for a while, maybe a few others, and everybody just goes to them. We get computing time from the cloud or something. We throw over problems. It does stuff for us. Guessing we're not going to be walking around with mini quantum computers in our phones anytime soon, but it is this notion that although there's competitors at the moment from the university perspective, once it gets built, is this going to be something that is heavily regulated and contained within a couple of institutions only?
Very good question. I suspect, at least in the beginning, you're going to have very, very few fault-tolerant quantum computers at scale. And if psi-quantum achieves what it says they're going to achieve, they may be one of only a couple in the world at this rate, to our knowledge, right? So you're right. There aren't going to be many out there, but I think in the initial I'm going to say that in the initial 5 years at least, it's so expensive and so complex to build a quantum computer. It's going to be delivered as a service, as IBM Q is today. So you will have broad access, and I actually think there's going to be a race to build quantum computers. So it might be 5 to 10 years before you start getting enough scale and enough companies who can build more quantum computers to then bring the costs down and make it more readily available. I think what concerns me is that we know that the minute there's a breakthrough, that so far as the threats are concerned, you're going to have threat actors who will have early access, right? Which will put the burning platform under everybody else. On the commercial side, is going to be a massive rush to get compute power around the world. And I think in the beginning, it's going to be pretty squeezed. You're right. I think there's only going to be a few big actors who will have a monopoly or a oligopoly in the beginning. But I think because of the value behind it, I think there'll be a lot of people building early as soon as they know what that should look like. So hopefully, I don't know, I'm an optimist, within 10 to 15 years, you'll have a lot more quantum computers. I'd like to think the prices will come down. And it'll be like any other computer, actually.
Yeah.
If you think about in the 50s and 60s, when they started to build our classical computers, you remember those, the vision of the scientists, and they're in a warehouse full of, infrastructure, and they're like, this is a computer, it's computing. And whereas now it fits in the palm of your hand. I'd like to think it's going to be a bit like that.
Absolutely. Other questions? We still have a few minutes. What piqued your interest in quantum, Claudine? I mean, how long have you been studying this for?
It's a bit of a passion pot for me.
Yeah?
A little bit more than a year. I've been, I actually know the PsiQuantum guys. I caught up with them a little bit more than a year ago, and them and a handful of other people sparked my interest, to be honest. And I started doing courses with NIT. And why? I think because I see it as the next big disruptor. And we still have time to learn about it, to educate ourselves. And I think it's, a bit like AI. It's old tech. It's been around for a very, very long time. But I think what's really interesting is you can see this. What do you want to call it? Like a milestone in time where you're going to have the ChatGPT 3 moments, right? For quantum computing, it's a little bit less subtle because it's going to, like, whoever can build the first fault-tolerant quantum computer will be a really big deal, and will be quite public. And I think that will be the ChatGPT 3 moment. And I actually think the implications of quantum computer are just so much broader and deeper from a threat perspective, but also from an opportunity perspective and the problems it can solve. So I think curiosity and the knowledge that it's going to deeply impact my field is probably where that all started.
Yeah, so when PsiQuantum does eventually build this billion-dollar machine in Bris Vegas, how are we going to decide who's going to get access to it first? Do we know? Have they discussed what the next step is then?
That is a very good question.
Ready for use?
I suspect, given the federal and Queensland governments have had a lot to do with that funding, they will have a say.
Yeah.
And so I doubt it will be all up to PsiQuantum. But I imagine, they will start off with a pretty appealing monopoly to begin with. If they achieve that.
You want them to solve some problems that
I
are uniquely Australian, right? That we have here at home, like how
that would be cool.
Could it help with modelling for housing and stuff like that in the early days? That would be a good application of it. Right?
I agree.
I would have thought straight up.
Couldn't agree with you more. Yeah, I couldn't agree. I don't know. That's a good question. I know for a fact that Jeremy and Terry are just heads down on the technical challenges they're trying to solve, and they have commercial people in their team. So yes, but they are an afterthought for them right now. But I'm sure the Australian governments have a pretty good idea of what's the ROI here.
Absolutely, it's a lot of money.